Hello guys, welcome to beta function introduction. So if you have been following right from the beginning of this series, I need you to tap yourself and give yourself a pat on the back. Yes, tell yourself you've done very well to have followed the introduction of gamma and beta functions up to this point, because in this video you are going to learn about beta function, but I am going to apply a lot of abstractions to minimize the difficulty that most students usually encounter with beta functions, and I'll tell you where that difficulty will arise. But not to bore you too much with my talks, let's dive in to beta functions. Now, beta function is also a special integral function. We've looked at gamma function in the past, so we saw that the gamma of a number n is evaluated as this special integral x to the n minus 1 exponential minus x dx. And I told us that the variable you're using for integration doesn't matter. It could be y, it could be t, it could be anything. The most important thing is that your integration takes this pattern. Is that okay? So we saw that the gamma of n is n minus 1 factorial, okay, for whole numbers. So we want to define the beta function. So by definition, beta takes in two parameters, unlike the gamma function. So we have the beta of what? Mn. Okay, so beta of mn is defined in this way. You have an integration from 0 to 1, then you now have x to the m minus 1 and 1 minus x raised to the power of n minus 1, so dx. So this is the definition of your beta function, and this is just what you need to know about beta functions. So mn is integral from 0 to 1, so you have x to the what? M minus 1 and 1 minus x to the n minus 1, so dx. So we want to look at a very important property of beta functions. So properties. So one of the properties of beta functions we'll be looking at is that beta of m comma n is still the same thing as beta of n comma m. So it's basically the same thing. It's still very much alike. Okay, so you shouldn't be scared that you're not actually getting, if you twist the positions, you will get something wrong. No, you shouldn't fret. So beta of n m is integral from 0 to 1, so you have x raised to the power of n, okay, minus 1, and you now have what? 1 minus x raised to the power of m minus 1 dx. So the reason why I said they are similar is because, let's say we put y equal to 1 minus x. You replace this particular place with y. So if you replace this place with y, what do you observe will happen to your integral? Okay, what will happen to the boundaries of the integral, and what will happen to the variable of integration? So quickly, the x or dy will be equal to minus dx. Okay, when you differentiate both sides with respect to x, the y will be minus dx. Then for the boundaries, you will find out that the boundaries will be when x is 0. Okay, when x is 0, we already have that y is equal to 1 minus x. So when x is equal to 0, if you slot in 0 here, y will be equal to 1. So when x equal to 1, if you slot in 1 here, y will be 0. So our integral will now transform to beta of n comma m is integral from 0 to 1. Sorry, I was too fast. So beta of n comma m is integral from, so since we are changing from x to y, it will be 1 to 0. Then our x is actually what, if you make x the shape of the formula here, x will be 1 minus y. Okay, x will be 1 minus y raised to the power of n minus 1. Then 1 minus y is 1 minus x is y according to this relation here. So you have m minus 1. So you have the x, and the x is minus 1 dy. Okay, so according to what we have, if you make the x the shape of the formula, you have minus 1 all over 1 dy, which is still the same thing as minus dy or minus 1 dy. So at the end of the day, my beta of n comma m is now this integral. Now, what did I tell us about negative signs? I told you that negative sign, or when you have a minus 1 and you have a definite integral, minus 1 works like magic on definite integral. It has the capability of reversing the direction or the polarity of your definite integral. So if I want to cancel out this minus 1, I'll make it affect the definite integral, so that instead of going from 1 to 0, we'll go from 0 to 1. Okay, so we'll have, if we just do some brief rearrangement, so you have y raised to the power of m minus 1, then you now have 1 minus y raised to the power of n minus 1, and you now have your dy. And if you look at it very critically, whether you want to use any variable you want or not, this is still the same thing as beta of m comma n that we defined above here. Is that okay? The only thing is that we used another variable. Some people like using t raised to the power of m minus 1, 1 minus t raised to the power of n minus 1 dt. So this is your beta of m comma n. Okay, so however you define it, you will still get your answer. So we have just proved that beta of n comma m is still very much equivalent to beta of m comma n, and all of them can be solved with this integration form. That's y to the m minus 1, then 1 minus y to the n minus 1, then you now have dy. Is that okay? Okay, or if you want to use x, whatever you want to use, it's still the same thing. So this is one of the crucial properties of beta functions. So number 2 is, I want to introduce us to the trigonometric version of beta functions. Now, beta function is defined as for two integers m and n, or for two real numbers m and n. We have 0 to 1, we have x to the m minus 1, then we now have 1 minus x to the n minus 1 dx. So this is the definition of a beta function. Is that okay? So we can also transform this to a trigonometric version of the beta function if we put x to be sine squared theta. So if you put x to be sine squared theta, definitely 1 minus x will be 1 minus sine squared theta, and we know that 1 minus sine squared theta is cos squared theta. Everybody should remember the golden identity that sine squared theta plus cos squared theta is equal to unity 1. Okay, so this is where we got this expression from. So x and what 1 minus x is respectively sine squared theta and cos squared theta if we make the replacement. Now we also have to evaluate the impact of making this substitution. How does this substitution affect the boundary of my integration? Okay, so x is equal to sine squared theta. Is that okay? 1 minus x cos squared theta, good and fine. Now if x is equal to sine squared theta, we have that theta will be sine inverse. If you make theta the subject of the formula, sine inverse of square root of x. Is that okay? So when you make theta the subject of the formula, theta is sine inverse of square root of x. So in other words, when x is equal to 0, we want to see what happens, what value will theta take. When x is equal to 0, so theta will be what? Sine inverse of square root of 0, which is sine inverse of 0, and this is also 0. So when x is 1, so theta will be what? Sine inverse of the square root of 1, which is the square root of 1 is 1, and sine inverse of 1 is what? Pi over 2 in radians, which is 90 degrees. So you have pi over 2, okay, or 90 degrees, pi over 2 radians, 90 degrees. So when we are transforming from x to angle domain, as from x to theta, we'll have that our integral will change from 0 to 1 to 0 to pi over 2. So let's also change the variable of integration. That's from changing from dx to d theta, and to do that you need to differentiate this with respect to theta. So dx will now give you, when you differentiate this one with respect to theta, you get 2 sine theta then cos theta. Of course, you should know how to differentiate sine squared theta with respect to theta. You bring down 2, then you write sine theta, then the next step is to differentiate sine theta, which is what? Cos theta. And you now attach a d theta to it at the end of the day. So dx is what? 2 sine theta cos theta d theta. So for our beta of m comma n, which we established as the integral from 0 to 1, x to the m minus 1, then 1 minus x to the n minus 1 dx, the integral has now transformed to this form, that beta of m comma n is integral from 0 to pi over 2, then x is sine square theta to the m minus 1, then 1 minus x is 1 minus sine square theta to the n minus 1, then dx is 2 sine theta cos theta d theta. Is that okay? So you have beta of m comma n to be integral from 0 to pi over 2. Then you now have, if you open this, you're going to have sine 2m minus 2 theta. Is that okay? You just use 2 to multiply it and you have it in this way. So dot cos, you have square theta, then you now have n minus 1, you now have 2 sine theta cos theta d theta. So going further, we have the beta of m comma n is integral from 0 to pi. You now have sine 2m minus 2 theta, and if you open these brackets, cos squared theta raised to the power of n minus 1 is still cos 2n minus 2 theta. That's when you open these brackets over here, and you now have 2 sine theta cos theta d theta. Now watch what happens. This 2 is a constant, so it comes out of the integration sign, so you have 0 to pi. Now sine theta is raised to the power of 1 here, and cos theta is raised to the power of 1. So if you apply the law of indices, sine 2m theta times sine theta, you're going to get sine 2m minus 2 plus 1 theta. Okay, because law of indices, for bases that are similar, the powers add up together. Is that okay? And I hope you know that this sine 2m minus 2 theta is still the same thing as sine theta, then all raised to the power of 2m minus 2. So this is just an easier way of writing it, so that is why I can easily add. Then this is cos 2n minus 2 plus 1 theta, because of this cos theta here. So you have cos theta interacting with what? Cos 2n minus 2 theta, then you now have your d theta. So at the end of the day, this is what we have as beta of m comma n in trigonometric form. You have the integral from 0 to pi, and you have sine 2m minus 2 plus 1 is minus 1 theta, and you now have cos 2n minus 1 theta d theta. So this is the trigonometric representation of what? Beta of m comma n. And some of us might be asking, why do we need a trig representation of m comma n? So pi over 2. I'm sorry, where did I lose that? I'm sorry, I was too fast. So some of us might be asking, why do we need a trigonometric representation for beta functions? Because there are some integrals that come in trigonometric form that we could express in terms of, this beta integral function. So it is very important to know how to convert a trigonometric integral to its beta representation, especially when that integral is from 0 to 90. That's a quarter wave integral. So this is the trigonometric representation of beta to 90 of beta function, of the beta function. So let's wrap up this video. I'll just say a couple of few things. Now, beta function has been summary. To summarize, beta function is defined as 0 to what? 1. Integral from 0 to 1. You have x to the m minus 1, 1 minus x to the n minus 1 dx. So we established that beta of m comma n is equivalent to beta of n comma m. We showed the proof, and for trigonometric cases we showed that the beta of m comma n is 2 integral from 0 to pi over 2. Then you now have sine 2 to the m minus 1 theta. You now have cos 2 to the n minus 1 theta d theta. So this is the trigonometric representation of beta function. Now, through the trigonometric representation of the beta function and through what we call reduction formulas in integral, we have been able to derive that this beta function will still be the same thing as you having an m minus 1 factorial times n minus 1 factorial divided by m, then m plus n minus 1 factorial. Is that okay? So this is what we have been able to derive by solving this integral. So when you solve this trigonometric integral, you're going to arrive at this particular case. So this is the factorial representation for beta functions. Now, I decided to abstract the process of carrying out this integration because that might make the fun of beta function, the fun of learning beta function, it might make you very weak and make you feel scared that beta function is difficult. So for the sake of that, I have decided to dedicate another video to showing how we can come from this integration to this particular point. So I'm going to release that video sometime in the future, and I'm going to attach the link to that video in this particular one. For those of you that will be watching this later in the future, I will show you how this was gotten through some special reduction formulas in integration, and you are going to appreciate the process. So this is the factorial representation of beta of m comma n. So but wait, we learned that gamma of a number n, for instance, is still the same thing as n minus 1 factorial. Gamma of an integer m is going to be m minus 1 factorial. Is that not so? So gamma of m plus n is still going to be what? M plus n minus 1 factorial. Does it make sense? I'm sorry. M plus n minus 1 factorial. So I can actually see that the beta and the gamma function actually are related to themselves. Is that okay? So beta of m comma n can be actually represented as m minus 1 factorial standing for what? A gamma of m. M minus 1 factorial is the gamma of m. Now an n minus 1 factorial is what? The gamma of n. Then an m plus n minus 1 factorial is what? The gamma of m plus n. Is that okay? Since we established that gamma of m is m minus 1 factorial and gamma of n is n minus 1 factorial and gamma of m plus n is m plus n minus 1 factorial. So the relationship between the gamma and the beta function is this. So if they ask you to prove that or show the relationship between the gamma and beta function, after you express this trigonometric form and after you just make a comment, let's say through reduction formulas in integration, we were able to evaluate this integral and we arrived at this point. So after arriving at this point, you can now define your gamma function. Gamma of an integer n is n minus 1 factorial, of an integer m is m minus 1 factorial. Therefore, the gamma of m plus n is also n plus n minus 1 factorial. So if we look at this very critically, I can see a gamma of m here. Let me use another ink so that you see how special it is. I can see a gamma of m in this first part. I can see a gamma of n, and I can see a gamma of m plus n in the denominator here. So this is how gamma function and beta function are related to each other. So in the next series of videos, we are going to dive into the full solutions to problems on gamma and beta function. So beta of m comma n in summary is what? Gamma of m times gamma of n divided by what? Gamma of m plus n. And someone can say this is an m minus 1 factorial, an n minus 1 factorial, then an m plus n minus 1 factorial. So thank you for watching this video. I hope you understood the introduction to beta functions, and from here onwards we are going to solve problems and I'm going to evaluate definite integrals that take the shape of gamma and beta functions. So any problem that you will be solving, literally you will see that you will need your knowledge of both gamma and beta functions, not just one alone. So it's important not to throw two of them away. You need to know two of them, and you will be all right. So thank you once again. Please like this video, like, subscribe, hit the notification bell to stay updated, share to your friends. Until next class, stay blessed. All right, bye.